Elliptical curve cryptography is often mentioned as another approach to doing asymmetric encryption for public key systems. And it's a good approach. RSA is certainly the most commonly used approach, but it is a patented piece of software. And so elliptical curve crypto is the alternative that is not encumbered by patents if that's an important piece of your infrastructure. ECC also provides the same kind of security using a somewhat shorter key length. It's a little bit more computationally intense in terms of actually doing encryption, but it can be basically the same level of security using a slightly shorter key length. Normally in class, I would go through and give you a little bit of intuition as to why elliptical curve crypto works from a mathematical standpoint, similar to what I've done with the RSA in the previous set of slides, and with the multiple prime numbers, that sort of thing. I can't really do that on this video simply because I don't have access to the same whiteboard type chalkboard setups, and I can't really record video doing that. But I'll simply say this. If you imagine that you have an ellipse, so something somewhat circle-like, and it has a point that goes through the origin of a plane, right? The 0, 0 point on a plane. One way to think about how this can be calculated very quickly in one direction, easily verified, and very, very difficult to reverse, is if I were to give you a total distance, and we'll think of the distance as my key, right? So imagine that the grid is a grid that outlines things in inches or something like that. If I were to give you a distance of, say, 79 inches, right? And starting at the origin point, traveling clockwise around this ellipse, this circular type ellipse, what point do you end on, right? That's a very easy thing to verify that they've actually ended on that particular point. But it's very hard to say how many times around the circle the person has traveled once they arrive on that point, right? So if you were trying to do encryption with a distance of 79 inches around this thing, around this circle, how many times around the circle do you go with 79 inches? You'd have to, in order to calculate that, you'd have to know the entire path the circle takes precisely. You'd have to be able to calculate the entire ellipse very, very precisely, and that is hard to reverse just based on the pieces of information that I've given you: a distance, a start point, and a stop point. There's lots and lots and lots of possible ellipses that, given that distance, the start point, and the stop point, you'd be able to achieve that same point. So that's a little bit of an overview as to the mathematics behind elliptical curve crypto systems. We also wanted to talk about quantum computers and what makes quantum computers so challenging for crypto stuff. The first piece of that is answering the question, what is a quantum computer? Well, in a modern computer, you are dealing with a bit that can either be 1 or 0, okay? In a quantum computer, you don't have bits. You have something called qubits, and they don't have just those two states. They can either be 1, 0, or a quantum superposition of all of the qubit states. And this last piece makes it a very, very fundamentally different way of building a computer system to base it on qubits. So a computer using Shor's algorithm, it's a famous algorithm defined for quantum computing, can efficiently do this number factorization in polynomial time, meaning that it's actually possible to do this in a computationally efficient fashion. And that has implications for crypto systems. In particular, quantum crypto would have to rely on our ability to measure properties of photons using Heisenberg's uncertainty principle, which makes senders and receivers in quantum communication very, very aware of eavesdroppers, right? Because as soon as something is measured, it becomes certain, right? The quantum superposition of the various qubit states becomes certain. It's resolved as soon as somebody tries to observe it. So quantum crypto can take advantage of this feature of quantum computers to make eavesdropping almost trivially easy to detect. Implementations of quantum crypto are still very much in the prototype stage. We don't really have practical quantum computers, and so therefore it's hard to think of practical quantum crypto systems. But there are lots of thought experiments going around, people trying to create these sorts of things in mathematics prior to the actual widespread deployment of quantum computers in order to have crypto when we first get there. We're still not to the point where this is ready for adoption. It may actually be practical in the next decade, 8 to 10 years or so, but it would definitely be a significant improvement over existing systems for encrypted communication. So that's the plausive side of quantum computers. The negative side is that current crypto systems are going to have some problems. In particular, asymmetric encryption is going to be a little bit tricky. So symmetric encryption, you'd probably just have to double the key length, because quantum crypto really only improves the factoring by the square root of the key length. So if you just double the key length of everything, it would be a lot easier to maintain symmetric encryption systems. Asymmetric encryption, it can still work, but definitely none of the systems that we use today, like RSA and elliptical curve crypto. So this is pretty devastating for the entire crypto ecosystem, because asymmetric encryption, although it is computationally problematic for us in terms of efficiency right now, it is mathematically solid in terms of practical implementations. And so we can use asymmetric encryption to exchange a symmetric key so that we get the efficiency gains of practical transit pipelines using symmetric encryption systems, and the security gains of knowing that we don't have to have this key exchange already done in advance. We can actually do key exchange on the fly with an asymmetric encryption system, just for the purpose of exchanging our symmetric key and then initiating a conversation using that symmetric key system. Well, that symmetric key can't be exchanged if the asymmetric encryption is busted, which is what would happen with a quantum computer, with widespread functional quantum computer systems. But there are alternatives to alternative asymmetric encryption systems, alternative mathematics that would not be as vulnerable to quantum computers' ability to use the qubit states, the superposition of qubit states, to rapidly do factorization. One of them is this Mikhaili crypto systems, which is very old. Another one is this much newer notion of lattice-based crypto systems. And there are other mathematical functions out there that may be good candidates, but let's just focus on lattice-based crypto, because that's the one that seems to be the most mature at the moment. Lattice-based crypto systems are based on computationally difficult problems involving mathematical lattices. So one example of a problem would be the shortest vector problem. Another would be the closest vector problem. And these are both, I think, reasonably good examples, kind of similar to the setup that I gave you just a moment ago with the elliptical curve, where we have some easy to verify, easy to compute stuff, and then an incredibly hard to reverse piece, right? So it's very hard to reverse a problem for which the closest vector that can be easily verified is available. So the two approaches, the two crypto primitives that we get from using lattice-based crypto systems that people were interested in prior to quantum computers becoming kind of a boogeyman for the industry are homomorphic encryption and functional encryption. And you may hear about these when people talk about lattice-based crypto systems. Homomorphic encryption is basically just a form of encryption that allows for computation on the ciphertext itself, right? So you have an encrypted blob, and you want to do some work on that encrypted blob without decrypting it. And homomorphic encryption allows for that sort of stuff. It can actually generate an encrypted result, which, after you decrypt it, matches the result of the operation that you would see had you just performed the operation on the plain text itself rather than on the ciphertext. So a very, very cool form of encryption. Functional encryption is a generalization of the public key encryptions that where you have this secret key allowing one person to learn a function of what the ciphertext is encrypting. It's kind of like a key exchange thing that would be very useful in terms of replacing AES or ECC, probably not AES, the RSA or ECC asymmetric encryption systems that we're currently using to do this key exchange piece. Okay, so that's really all I wanted to talk about with quantum computers and sort of their impact on modern crypto systems.